Hello students, in this session we will study the partial differentiation of functions of function and implicit function. We have studied total differentiation of u is equal to f of xy, where x and y were independent variables and also independent of each other. In this talk, we first consider the case of dependent variable. Let x equal to ft, y equal to ht, where t is the independent variable. Thus, u is a function of x and y are functions of t. We try to answer what is the derivative of u with respect to t. Let u be wheat produced by x labor on y land. Now assume that the number of labor x and area of land y depend on the amount of money t that is on hand. Thus, when there is a small increase in t, it will increase in x and y, which results increase in u. So, we need to study how much change in u will occur with a unit change in u. Denote this by du by dt. We know that del u over del x is the change in u due to a small change in x keeping y constant. Also, dx by dt denotes the change in x due to a small unit change in t. Thus, del u over del x dx by dt will be the amount of change in u due to a small change in t that is transmitted through x. Similarly, del u over del y into dy by dt will be the amount of change in u due to a small change in t that is transmitted through y. Therefore, the change in u due to a small change in t will be linear sum of these two effects as du by dt is equal to del u over del x into dx by dt plus del u over del y dy by dt, which is equal to ux dx by dt plus uy dy by dt. Let us take an example. Find the total derivative of u with respect to t if u is equal to x square plus y square, x equal to t square and y is equal to t square plus 1. We know that du by dt is equal to ux dx by dt plus uy dy by dt, where ux is equal to 2x, uy is equal to 2y, dx by dt is equal to 2t and dy by dt is equal to 2t. So, du by dt is equal to 2x into 2t plus 2y into 2t is equal to 4t into x plus y. Example, find du by dx when u is equal to x square plus y square and y is equal to 2x. Set y is equal to 2t and x equal to t. So, du by dt is equal to ux dx by dt plus uy dy by dt is equal to 2x into 1 plus 2y into 2, which is equal to 2x plus 4y. Note, since x is equal to t, we have du by dx is equal to ux dx by dx plus uy dy by dx is equal to ux plus uy dy by dx, which can be used when x and y are not independent. Interpretation: the change in u is due to increment of x is the sum of ux, which is the change in u when there is an increment in x treating y constant, and change in u due to increment in y, which in turn is due to the change in x. Let us take an example. Consider v is equal to pi r square h, where r is the radius, h is the height and v is volume of a cylinder. Let r is equal to t square and h is equal to t square where t is time, what will be the rate of increase in the volume of the cylinder per unit of time? We want to compute dV by dt is equal to Vr dr by dt plus Vh dh by dt. Now, Vr is equal to 2 pi Rh and Vh is equal to pi r square. Dr by dt is equal to 2t and dh by dt is equal to 2t. Then, dV by dt is equal to 2 pi r h into 2t plus pi r square into 2t is equal to 6 pi t raised to 5. Note, for u is equal to f of x, y, z and so on, x equal to gt, y is equal to ht and so on. Du by dt is equal to ux dx by dt plus uy dy by dt plus uz dz by dt and so on. Two or more independent variables case. Let u is equal to f of xy, x equal to g of st, y is equal to h of st, then del u over del t is equal to ux del x over del t plus uy del y over del t. Del u over del x is equal to ux del x over del s plus uy del y over del s, where del u over del t is the total derivative of u with respect to t when s is considered to be constant. Let us see an example. Find del u over del t if u is equal to x square plus y square, x equal to t square plus s square, y is equal to t square minus s square. We have del x over del t is equal to 2t, del y over del t is equal to 2t, ux equal to 2x, uy is equal to 2y. So, del u over del t is equal to ux del x over del t plus uy del y over del t, which is equal to 2x into 2t plus 2y into 2t, which is equal to 4x plus y t. Note, result holds for n variables. Theorem: given u is equal to f of xy, the differential of u is du is equal to fx dx plus fy dy regardless of whether x and y are independent or not. Proof: we have seen the result when x and y are independent. We need to show that the differential du holds when x and y are not independent. Let u is equal to f of xy, x equal to g of st, y is equal to h of st, then del u over del s is equal to ux del x over del s plus uy del y over del s. Del u over del t is equal to ux del x over del t plus uy del y over del t. Multiply first equation by ds and second by dt and add them. Then left hand side would be del u over del s ds plus del u over del t dt. Since u is equal to f of xy, which is equal to f of g of st h of st, we set du is equal to us ds plus ut dt. Right hand side after addition is ux into del x over del s ds plus del x over del t dt plus uy into del y over del s ds plus del y over del t dt. But dx is equal to del x over del s ds plus del x over del t dt and dy is equal to del y over del s ds plus del y over del t dt. Therefore, right hand side is equal to ux dx plus uy dy. Combining left hand side and right hand side gives du is equal to ux dx plus uy dy, which is differential of u is equal to f of xy. Let us take an example. Let u is equal to f of q1 q2 and p1 q1 plus p2 q2 is equal to m. where u is a utility function with goods Q1 and Q2, m denotes income, and P1 and P2 are the prices of Q1 and Q2. The second equation is known as budget equation. Find the marginal utility of Q1, which is del u over del Q1 and also del square u over del Q1 square, which denotes the rate of change of marginal utility of Q1. Write Q2 equal to m minus P1 Q1 over P2. Then Q1 is the independent variable and we have du over dQ1 is equal to uQ1 plus uQ2 dQ2 over dQ1. Now dQ2 over dQ1 is equal to minus P1 over P2. Therefore, du over dQ1 is equal to uQ1 minus uQ2 into P1 upon P2. Student is asked to compute del square u upon del Q1 square. Higher order differentials. Let u is equal to f of xy, x equal to gt, y equal to ht, where t is the independent variable. Then du by dt is equal to ux dx by dt plus uy dy by dt. Del square u over del t square is equal to del by del x, ux dx by dt plus uy dy by dt dx by dt plus del over del y ux dx by dt plus uy dy by dt dy by dt. First term is equal to del over del x ux dx by dt plus uy dy by dt dx by dt, which is equal to uxx dx by dt plus ux del over del x dx by dt plus uyx dy by dt plus uy del over del x dy by dt dx by dt. Here ux del over del x dx by dt is equal to ux del over del t dx by dt dt by dx, which is equal to ux d square x over dt square into dt by dx, and uy del over del x dy by dt is equal to 0. Therefore, first term is equal to uxx dx by dt whole square plus ux into d square x upon dt square dt by dx dx by dt plus uyx dy by dt dx by dt, which is equal to uxx dx by dt whole square plus ux into d square x upon dt square plus uyx dy by dt into dx by dt. Similarly, second term is equal to uyy dy by dt whole square plus uy d2y upon dt square plus uxy dx by dt into dy by dt. So, d square u upon dt square is equal to uxx dx by dt whole square plus uyy dy by dt whole square plus ux d square x over dt square plus uy d square y over dt square plus 2uxy dx by dt into dy by dt. Let's take an example. Given u is equal to x square plus xy plus y square, x equal to t cube plus 1, y equal to t minus t cube. Du by dt is equal to ux dx by dt plus uy dy by dt, ux equal to 2x plus y, uy is equal to x plus 2y. Uxx is equal to 2, uxy is equal to 1, uyy is equal to 2, dx by dt is equal to 3t square, dy by dt is equal to 1 minus 3t square, d square x upon dt square is equal to 6t, d square y upon dt square equal to minus 6t. Du by dt equal to 2x plus y into 3t square plus x plus 2y into 1 minus 3t square. D square u over dt square is equal to uxx into dx by dt whole square plus uyy dy by dt whole square plus ux into d square x upon dt square plus uy into d square y upon dt square plus 2uxy dx by dt into dy by dt, which is equal to 30 t raised to 4 minus 42 t square plus 60 plus 2. Note, when x equal to gt and y is equal to ht are linear, d square x by dt square equal to 0 and d square y over dt square is equal to 0. Hence, d square u over dt square is equal to uxx dx by dt whole square plus uyy dy by dt whole square plus 2uxy dx by dt into dy by dt. Higher order derivatives when let u equal to f of xy, y equal to gx, where x is the independent variable and y is dependent variable. This type of functional form occurs most in economics. We have du by dx is equal to ux plus uy into dy by dx, d square u upon dx square is equal to del over del x, ux plus uy dy by dx plus del over del y, ux plus uy dy by dx, dy by dx, which is equal to uxx plus uxy dy by dx plus uy del over del x dy by dx plus uxy plus uyy dy by dx plus uy del over del y dy by dx dy by dx is equal to uxx plus 2uxy into dy by dx plus uy into d square y by dx square plus uxy plus uyy into dy by dx whole square. Example, find du by dx and d square u by dx square for u equal to x square plus 2y square, y is equal to 4x minus 1. We have du by dx is equal to ux plus uy dy by dx. d square u upon dx square is equal to uxx plus 2uxy dy by dx plus uy d square y upon dx square plus uxy plus uyy dy by dx whole square. dy by dx is equal to 4 and d square y upon dx square is equal to 0. ux equal to 2x, uy is equal to 4y, uxx is equal to 2, uxy is equal to 0, uyy is equal to 4. Therefore, du by dx is equal to 2x plus 16y, d square u by dx square is equal to 2 plus 4 into 4 square plus 2 into 0 into 4 plus 0, which is equal to 66. Extension to 3 variables. Given u is equal to f of x, y, z and z equal to g of x, y, du by dx is equal to ux del x over del x plus uy del y over del x plus uz del z over del x is equal to ux plus uz del z over del x. d square u upon dx square is equal to del over del x ux plus uz del z over del x by del x plus del over del y use x plus uz del z over del x del y over del x plus del over del z ux plus uz del z over del x over del x. But del y over del x is equal to 0 and del over del z over del x is equal to 0. So, d square u upon dx square is equal to uxx plus uzz into del z over del x whole square plus 2uxz del z over del x plus uz into del square z over del x square. Similarly, du by dy is equal to uy plus uz into del z over del y. d square u upon dy square is equal to uyy plus uzz into del z over del y whole square plus 2uyz into del z over del y plus uz into del square z over del y square. Example, find du by dx and d square u by dx square for u is equal to x square plus y square plus z square and z equal to 3x minus 2y. Du by dx is equal to ux plus uz into del z over del x, which is equal to 2x plus 2z into 3, which is equal to 2x plus 6z. D square u upon dx square is equal to uxx plus uzz into del z over del x whole square plus 2uxz del z over del x plus uz into del square z over del x square, which is equal to 2 plus 2 into 3 square plus 2 into 0 into 3 plus 2z into 0, which is equal to 20. Homogeneous function. Let us understand concept of homogeneous function through example. Let f of xy is equal to x square minus y square. If we replace x by tx and y by ty in the function where t is a positive constant, then f of tx ty is equal to tx square minus ty square is equal to t square into x square minus y square, which is equal to t square into f of xy. For f of xy equal to x cube minus y cube, we have f of tx ty is equal to t cube into f of xy. By induction, for f of xy equal to x raised to n minus y raised to n, f of tx ty is equal to t raised to n f of xy, then we say that f is homogeneous. For example, if f of xy is equal to x square plus xy minus 3y square, then f of tx ty is equal to t square into f of xy. A function is said to be homogeneous function of degree n if f of tx ty is equal to t raised to n f xy. Example, f of xyz equal to x plus y upon z. We have f of tx ty tz is equal to tx plus ty upon tz is equal to x plus y upon z, which is equal to t raised to 0 into f of xyz. So, f is homogeneous function of degree 0. Properties of homogeneous function. Consider a homogeneous function of degree n as u equal to f of xy, then f of tx ty is equal to t raised to n f of xy. Since t takes any value, let t equal to 1 upon x, then f of tx ty is equal to f of 1 y upon x, which is equal to g of y upon x. That is, f of tx ty becomes a function g which has variable y upon x. Also, t raised to n f of xy is equal to 1 upon x whole raised to n into f of xy. Comparing last two form gives f of xy equal to 1 upon x raised to n into g of y upon x. In general, if u is equal to f of x, y, z and so on, f of tx, ty, tz and so on is equal to t raised to n into f of x, y, z and so on. F of x, y, z and so on is equal to x to the power n into g of y upon x, z upon x and so on, which is equal to y to the power n into h of x upon y, z upon y and so on, which is equal to z to the power n into k of x upon z, y upon z and so on. Example, consider a homogeneous function of degree 3 as f of xy equal to x square y minus xy square. Then f of xy is equal to x cube into g of y upon x, where g of y upon x equal to y upon x minus y square upon x square. If f of xy is a homogeneous function of degree n, the kth derivative of f is a homogeneous function of n minus k provided the derivatives exist. Consider f of xy is equal to x square y square plus xy cube, then f is a homogeneous function of degree 4. fx equal to 2xy square plus y cube is a homogeneous function of degree 4 minus 1, which is equal to 3. fxx is equal to 2y square is a homogeneous function of degree 4 minus 2, which is equal to 2. Euler's theorem. Euler's theorem is obtained from homogeneous function and useful for marginal productive theory. It is also known as adding up theorem. Let u equal to u of xy be a homogeneous function of degree n, then xux plus yuy is equal to nu. Note, ux and uy are partial derivatives of u with respect to x and y respectively. Proof. U of xy is a homogeneous function of degree n, so u of tx ty is equal to t raised to n into u of xy. Del over del t of left hand side is equal to del u tx ty upon del tx into del tx upon del t plus del u tx ty upon del ty into del ty upon del t, which is equal to x u tx plus y u ty. Del over del t of right hand side is equal to del t raised to n over del t u xy plus t raised to n into del u xy over del t, which is equal to n into t raised to n minus 1 u xy plus 0, which is equal to n into t raised to n minus 1 u xy. Therefore, x u tx plus y u ty is equal to n t raised to n minus 1 into u xy. As t is any number, put t equal to 1. So, x ux plus y uy is equal to n u of xy. In general, for more than two variables, x ux plus y uy plus z uz plus and so on is equal to n u of x, y, z and so on, where n is the degree of homogeneous function. Let us take an example. U of x, y, z is equal to 3x plus 2y minus 4z is a linear homogeneous function. Then, by Euler's theorem, x ux plus y uy plus z uz is equal to 1 into 3x plus 2y minus 4z. Check ux equal to 3, uy equals to 2 and uz is equal to minus 4. Therefore, left hand side is equal to 3x plus 2y minus 4z, which is equal to right hand side. Example, u of xy is equal to x square minus 3y square is a homogeneous function of degree 2. By Euler's theorem, x ux plus y uy is equal to 2 into x square minus 3y square. Check ux equal to 2x, uy equal to minus 6y. Therefore, left hand side is equal to 2x square minus 6y square, which is equal to 2 into x square minus 3y square, which is right hand side. The adding up theorem states that the product will be exhausted if factors are paid according to the marginal productivity theory. That is, if q equal to f of ab, where q is output and a and b are inputs, then q is equal to AFA plus BFB, where FA and FB will be the marginal products of A and B. Let us see how it works for a linear homogeneous function. The Cobb-Douglas is such a function defined by P is equal to B into L raised to K into C raised to 1 minus K, which is equal to F of LC. The adding up theorem gives LFL plus CFC is equal to P. Left hand side is equal to L into BK L raised to K minus 1 C raised to 1 minus K plus C into B 1 minus K L raised to K C raised to minus K, which is equal to B into L raised to K C raised to 1 minus K, which is equal to right hand side. This suggests that average costs and hence marginal costs are constant. Partial elasticity. Let QA is equal to U of PA PB, where QA is the quantity of good A demanded, PA is its price, and PB is the price of good B. Price elasticity is defined as eta, which is equal to minus del QA over del PA into PA upon QA. This is considered as the partial elasticity of good A with respect to PA. Similarly, the partial elasticity of good A with respect to PB is given by eta is equal to minus del QA over del PB into PB upon QA. Example, QA is equal to 50 minus PA minus 4 PB. Then elasticity with respect to PA is eta is equal to minus del QA over del PA into PA upon QA. We have del QA over del PA is equal to minus 5. So, eta is equal to minus 5 into PA upon 50 minus 5 PA minus 4 PB. For PA is equal to 5 and PB is equal to 5, eta is equal to 5 into 5 upon 50 minus 25 minus 20, which is equal to 5. Let us summarize what we have learnt. Del U over del X is the change in U due to a small change in X keeping Y constant. Del X over del T denotes the change in X due to a small unit change in T. Del U over del X into dx by dt will be the amount of change in U due to a small change in T that is transmitted through X. Del U over del Y into dy by dt will be the amount of change in U due to a small change in T that is transmitted through Y. The change in U due to a small change in T will be linear sum of these two effects, and it is called the total derivative of U with respect to T. For U is equal to f of xy, x equal to gt, y equal to ht, where t is the independent variable, the second order total differentiation is given by d square u upon dt square is equal to uxx dx by dt whole square plus uyy dy by dt whole square plus ux d square x upon dt square plus uy d square y upon dt square plus 2uxy dx by dt into dy by dt. A function is said to be homogeneous function of degree n if f of tx ty is equal to t raised to n f of xy. Euler's theorem. Let u is equal to u of xy be a homogeneous function of degree n, then xux plus yuy is equal to nu. Let qa is equal to u pa pb, where qa is the quantity of good A demanded, pa is its price, and pb is the price of good B. Price elasticity is defined as eta, which is equal to minus